Professor Eda Goki. In the current terms or US terms, it would be Goki Eda. First of all, congratulations for your recent Presidential Young Scholars Award this year. And I think many people don't remember you actually got the NUS Young Scientist Award last year. Again, congratulations.
It was actually this year.
What's that?
It was actually this year.
Even the NUS one?
The NUS one was this year.
Okay. So I'd like to ask you, as you know, this is a series to introduce our scientists and engineers to the NUS community, but also to the larger community at large. So I've got just a few questions to ask you. I see from your award, and actually from just talking to you informally, that you're really very interested in basically 2D structures and how these structures with certain unique will confer certain unique properties either in photovoltaic or optoelectronics, but also you had one where you actually had electrochemical activity. So let me just ask you to summarize for a lay audience. What got you really excited about exploring these, what would be surface phenomena or 2D phenomenon in this area of physics?
Well, I think the concept of this nanoengineering and nanotechnology has been around for a long time. But what I liked about these 2D materials is that these materials sort of form naturally. They sort of exist in nature. So we can extract out these highly crystalline two-dimensional sheets that are literally a few atoms thick. And surprisingly, we know very little about how they behave electrically, optically, mechanically, or thermally. So we really need to start from the basics to understand their generic behaviors. And one of the things, well, there are a few things that we focused on, but one of the things that we started studying is the optical light-matter interaction, the interaction between light and two-dimensional materials. And another thing that we looked at was well, how chemically we can induce structural changes in these two-dimensional materials. And that's sort of just of what we are doing now.
Good. Now you mentioned something that I didn't quite get. You said that these 2D materials actually form quite naturally, but I'm an old-fashioned engineer, and I did chemistry and physics also, but we're used to, let's say, bulk materials. Now, how do the bulk properties affect or distort the simple surface properties that you see?
Well, precisely speaking, they don't form true two-dimensional structure naturally. So, but what we find in nature is layered materials.
Okay.
Right? So layered materials in which the building blocks are these chemically bonded sheets, and they just simply like to stack up into three-dimensional structure. So that three-dimensional stack is what we find naturally. When we break them into individual pieces or their basic building blocks, that's where we have the two-dimensional structure. And how these individual layers differ from the bulk three-dimensional structure is quite subtle in a way. But one thing you can say is that it's just a sheet with like atomically thin thickness. So effectively, all you have is a surface. You don't have any volume. So you can imagine that whatever you do from the top or from the bottom will affect the entire sheet.
The lattice itself.
Right. So it's remarkably sensitive material in a way. So if we do anything chemically or optically or electrically, it responds quite dramatically.
Yeah, more dramatically without the bulk to
Right.
interfere. That's fascinating. which then brings me as an engineer into the more practical application. Because I've talked to, I think, the people in the Graphene Research Center is also now going from carbon 2D materials to other 2D materials. Practically, if you have this very interactive structure to light or electrons or other materials, other chemicals, when you look at both the optoelectronics, when you look at the possible PV applications, and then the more chemical ones on, let's say, decomposition of water, electrolysis, how would you project as to which of these three will go into the market a lot sooner than the others? That means if you had to pick a winner, I know scientists and engineers, engineers do that. Scientists don't like to do that. But if I were to ask you, where do you see the applications coming in faster? Optoelectronics, PV, or the more traditional chemical reactivity type?
Well, I think, as you say, it's always very difficult to predict the future. But when we talk about applications, I think there are a few things that you have to think about. One is there competing technology that's available already in the market? And in terms of optoelectronics and electronics, there's a very mature technology available right now, and coming up with a new technology that would immediately replace the existing, or supplant the existing technology is very difficult in the short run. On the other hand, there are some applications that could be unique to two-dimensional materials, and the second thing I was going to mention is that you want to have your material to be available in large quantity. Otherwise, you cannot think about applications. And so, from those 2 points, from those 2 perspectives, I think the chemical applications or catalysis application is quite appealing, because we know how to make these two-dimensional materials in relatively large quantities, although they may not be structurally well defined, but they do their job, and they can be produced in a scalable manner. So from that perspective, I think electrochemical or chemical applications are more prominent at this point.
Yeah, in that sense, then I would agree with you, because my background is in catalysis.
Okay.
And when we do a lot of chemical catalysis, it's always the molecular site. And can you put it on a substrate which then doesn't distort the peculiarity of that molecular site or that 2D structure?
Yeah, well, I think if you start talking about substrate, it's another whole level of research. But I think from simply looking at the surface to volume ratio, there's just a huge amount of surfaces available in these two-dimensional structures. So from that basic argument, even if the overall per unit surface area performance might be inferior to some of the existing ones, but if you can produce an extremely high, large surface area material, then I think that there's a chance in replacing existing technologies.
Fantastic. Again, thank you very much for this quick tutorial. Great, thank you.